This morning,
yes.
We have Stefan Hollands.
Nee, lass mal, ich glaube, das gibt vielleicht Interferenz.
From Göttingen, and he's been a number of years in the United States. And also, we heard his name many times this morning. So we're looking forward to hearing what he has to say about perturbative quantum field theory via vertex operators.
Thank you, Arthur. Yes, thanks very much to the organizers, Henning and Dorothea and Detlef and Pierre and all the others who put in so much work to this meeting for inviting me and in fact giving me the opportunity to speak on something on the topic of my choice. And I have chosen some sort of more mathematical work to present that to you, and it has this long title. Here's the pointer, and I was tempted to. So it has certain buzzwords there: perturbative quantum field theory and vertex algebras. And what I'll try to explain to you a little bit is how sort of want to present to you a viewpoint on quantum field theory that I guess was explained to some extent in the talk by Bob Wall this morning. But I want to explain it and sort of give it a slightly different twist, and sort of emphasize maybe a little bit more the mathematical structure behind this. So this three cartoon pictures. This is a collider experiment with two particles or smashing together, I suppose. And these two are supposed to stand for the pillars of quantum field theory as they are probably viewed by many people. That is, one is sort of diagrammatic expansions to calculate things, and the other ones is symmetries. I mean, this is the Platonic solids, and the famous drawing by I suppose I've forgotten who's the artist there. Anyway, so symmetries play a key role in constructing models, and it's sort of the combination of the two that gives the whole thing a considerable power. But this is not quite the viewpoint of this audience, I suppose. And I want to say maybe a little bit how they can be married to some extent, and maybe shed some new light on this. Anyway, here's my outline. I won't want to go too much into this. So there, as you know, there are different approaches to quantum field theory, QFT. A very popular one and absolutely elegant one, in my opinion, is the path integral. It has many advantages. I think the key advantage is that it's very easy to remember, because you know, that formula isn't so long, and it's an integral, something we're used to. It's supposed to be a functional integral with where you integrate a quantity related to the classical theory, the action of the field configuration over the space of all configurations, and to get your Schwinger functions, or ultimately Weidmann functions, you may want to put in some sort of source term. And anyway, I mean, the key advantage probably is that it's easy to remember, and but it's also very nice because it's very closely related to the classical theory. And I think psychologically it's also, it has a definite advantage that it's an integral after all. It's a functional integral, but integrals are something that we grow up with. And the fact that it's an integral over an infinite dimensional space is not maybe such a big psychological hurdle as imagining that things don't commute and have some crazy probability interpretation, as is sort of what is emphasized in other approaches to quantum field theory or quantum mechanics. This integral is not at all easy to define. I mean, if it were, then we all would be a lot easier off. And in fact, a lot of beautiful work has been done on this. So particularly in the formulation where you continue this Lorentzian type expression to a Euclidean signature. You can actually, it turns out, you can make non-perturbative sense of this expression, and this has led to some absolutely beautiful mathematical work with discovery of beautiful combinatorial expansions of a completely new type, lots of lots of new tools from analysis have come out of this, and this is the work of Glim and Jaffe and Bridges and also John Demock and Riverso and many other people, which I won't go into. And the other use of this is that it's quite easy to formally derive lots of identities in quantum field theory. That is, you get some sort of understanding of anomalies. You can derive things like word identities or all that kind of stuff in a relatively easy way, but it's formal. And the third advantage, I think, is that this also leads to the standard perturbative expansion if one sort of does the standard split of S into a free and an interacting part and just expands out the exponential. I think it is a very slick way to derive this just from this integral. This is not the only approach, though. There's people out there. I mean, I guess that approach is not so popular anymore, but it has come up again, as you probably heard in the talk by Gandalf, where you somehow put an S matrix on top of everything, and you try to derive things from an S matrix. And that too has nice advantages. I mean, it certainly has a clear-cut relation to scattering experiments, which after all are the most interesting experiments, I suppose, done with quantum with elementary particles. The S matrix, if you add in the magic formula of LSZ and Gell-Mann and Low, you get sort of nice graphical expansion for this. And also it's used in some people, for example, in string theory for a long time. The S matrix was all you had, and you didn't have any sort of analog of local fields. So some people certainly would take the view that the S matrix is the key thing to consider. Why we are here? We're here not to celebrate these two ideas. We're celebrating another circle of ideas, and which I think can be called algebraic approaches, because actually, after all, we've already, I think, heard in those talks. I mean, these approaches, they have many facets, and there are many different variants thereof. One of the, well, I think I personally like. Obviously, we all know sort of the style of these algebraic approaches that was pioneered by Rudolf Haag and then carried forward by many other very brilliant people. There are other variants, though, of this. I think that also can be thought of as in essence algebraic, and I think those approaches are quite used actually by many people, and they have to do with sort of basically putting the operator product expansion taking that to take the center stage in the scheme of things, and that was basically proposed by Wilson, and one of his very famous early papers is called the I think it's called non-Lagrangian models of current algebras. So I think that title suggests that he too probably thought about thought of this as some sort of algebraic structure that is behind field theory. At his time, probably current algebras were very popular. So I think that's the current algebra bit. I think that's not so much the key thing, but it's sort of the algebraic twist, the algebraic flavor of this expansion that I think puts it in this category. Anyway, so I think Haag, though, well, he had another, as you all know, of course, he had another view of this, and he thought in terms of C-star algebras and nets of C-star algebras, and I think really this was a great idea, and probably still very much ahead of his time, certainly, and probably still ahead of our time in a way. And I think one should maybe be open to the idea that there are many ways. I mean, if I think the key thing is that you think of field theory as having some sort of algebraic description, but what exactly that is, I think one should be maybe quite open about at this stage. Anyway, so in this talk I want to focus on this sort of operator product expansion and what the algebraic content is of this. And so this expansion, I said already, was proposed first by Wilson, and but then I think his was just a proposal, and then Zimmermann and together also with Wilson in some very famous papers, they showed that this actually works in perturbation theory, which is actually a very non-trivial thing. But anyway, the idea is basically, and I think that was already pointed out in the talk by Bob, you have a sort of a typical product of point-like fields. So you're dealing with point-like fields in this approach mostly, and you take an expectation value, and so these labels A here, I think I'm using a slightly different notation here. Labels A, yes. So by phi A, I mean this is a generic symbol for a composite field. So you may think of this as something like d phi, nu phi, p to the 7th, or t mu nu, or if you have a current, j mu, or j mu, j nu, whatever. So whatever comes to your mind. The label A is supposed to differentiate between all these fields, and also should be sort of incorporating any tensor or spinor or other indices you have. And then the idea is this operator expansion is some sort of a factorization. So you say that this kind of complicated function factorizes in a sum of products of so-called coefficients which depend on the field species that you're talking about, and certain other quantities which involve the state. And these things are supposed to not depend on the state, and so that all the dependence on the state is really in these quantities here. And it's sort of, as this wiggly tilde, I suppose it's called, suggests, it's not usually thought of as an equality, mainly because one doesn't really expect this thing to converge. And basically the idea is you have an expansionist going on here, but in physical terms, the expansion parameter, so there's a small parameter, is not something like a coupling or h bar or something. The small parameter is, in a sense, the ratio of the typical distance here between the points and the energy scale of the state. So you want that distance to be much smaller than the energy scale of the state, and then that's a small parameter, and then that's a good expansion. Anyway, there has been lots of applications of this expansion, sort of in Yang-Mills theories. It's applied to deep inelastic scattering, because these things can be calculated very reliably in perturbation theory, whereas these things have non-perturbative information which can't be calculated in any way at all. And so you just say that this is something you make some reasonable guesses for, or you parameterize, take this as free parameters, and then you get a nice expression for the endpoint function, say, of currents. And that's the idea. It's also extensively used in two-dimensional conformal field theories, where this operator expansion also takes central place. So I want to then basically take the viewpoint that these things are like the structure constants of an algebra, or the structure functions or structure distributions. I'm not very precise at this stage, as was advertised also in the talk by Bob, and I have the same philosophy here, and to appeal to the mathematicians, I'm going to do something that they love, and I use an index-free notation, which makes everything look much nicer. So instead, the C, so I declare that the fields, they're just names. They're not, you're not supposed to think of them as operators or something, just as abstract generators of an algebras. And so these span, you declare them to be basis vectors of an abstract vector space. And this thing is then for each configuration of points x1 through xn, a tensor or a linear map from the n-fold tensor product of this space V, whose basis elements are in one-to-one correspondence with the field to V. So the V here is the upper index here, and the other copies of V are the lower index here. So I'm working in a Euclidean form, in a Euclidean version of quantum field theory. I'm not working on curved space at all in this talk. Just I think everything can be generalized to curved space, but I just want to leave out that complication. And I want to basically say that these things are the data of some mathematical structure, and so these data basically are the data of some sort of algebraic structure. I don't say an algebra, it's something like an algebra, and so they're supposed to have some nice properties, some covariance under the obvious representation of the p-dimensional Euclidean group on this space, and then you have some. If you apply a permutation to these tensor factors and points, you're going to have some local commutativity or anti-commutativity, which is, think of this space V as a graded space, really. The space V is graded in many ways. One way is sort of a Z2 Bose-Fermi grading. And then you want them to be defined for non-coincident points, and you want them to be real analytic functions in these n variables from Rd. And you have some notion of Hermitian adjoint, another operation on this V, which is supposed to be consistent, and so on. The main point is what is the analog of the associativity condition. And that's what I'm going to describe. And I want to see how this leads to a new formulation of perturbation theory and how it can be used as a constructive tool. And so what is this consistency condition? I think we've heard about this morning. I'll tell you again. So the idea is, so it's a heuristic derivation. It's not a mathematical proof. You want to just arrive at some condition now that you can reasonably impose. So you just say you have, let's say, as usual with some sort of associativity, you don't consider the product of two things, but of three things. And you have three fields that are at three different points. And then you can place the brackets in different ways, as you do when you try to test an associativity law. And so what the bracket means here is that you perform the operator product expansion of these things, and then subsequently you perform the operator product expansion of the result with this, and this is the other way around. And you just say this should be equal. And so if you write it in terms of these coefficients, you're going to get a quadratic condition, which like everyone, it has the same flavor as the Jacobi identity in Lie algebras or something, just that it has these additional dependencies on the points. And for reasons, because of these sort of hierarchy of energy and things like that I briefly alluded to, you only expect this to converge on this domain. So R1, 2 is the Euclidean distance between point 1 and 2, and so on. So this is an infinite sum over all fields C, and then this is supposed to be an inequality on this domain. Now, if you're not in this domain, you're not expecting any of these sums to converge. So it's really only an equality on this domain. So as the philosophy again in this talk is to say that now now you could say that now maybe Arthur Jaffe would say he has the path integral and he makes sense of it, and then afterwards if I come and say I'm very interested in the operator product expansion, he proves that there is such an expansion, and I don't want to do that. I want to say that this is supposed to be my starting point. So these things are supposed to be what I have to calculate, and I forget about the whole rest. And then that is the idea is then in that way, if you're given these things, you're given the algebra. Okay, so now this is the same consistency condition written in this coordinate invariant, so this index-free notation. I think it's a lot easier to remember. And now this ID is the identity on this space V, and this is viewed abstractly, as I said before, as a mapping from V cross V to V, because this has two down indices. These are these two copies, and one up index, and that's this copy. It's an index-free notation. And it's, again, an identity that's valid here. So this is my starting point. And I want to say that my viewpoint here is that if you can find a solution to this quadratic equation, you've constructed a quantum field theory. That's my viewpoint. Just as if you can find a solution to the Jacobi identity, you've given a Lie algebra, right? So that's kind of the idea. And so normally in algebra, you can ask, this is associativity, AB the same as ABC here, and you can for example ask whether your sort of higher associativity conditions are independent of this one, or whether they're actually new conditions. Probably when you're in your sort of undergraduate algebra course, I mean that's something you prove that once you have this relation for for a product of three guys, you conclude that such equations automatically hold. So they're not new conditions. But in this context, it's actually not quite so clear what happens. And actually, it is though true that in some sense there would be other higher order associativity conditions, but in some sense they can be all reduced to this one. So mathematicians call this a coherence theorem. So it's a McLean coherence theorem. There are tons of such theorems. For algebras, that's the simple one, and there are more general mathematical structures, a bit like algebras, where such theorems hold. And here's another structure where this kind of thing holds. Okay. Right. So now the interesting question is, of course, how on earth are you going to get any solution to this? Because this is a quadratic equation. If you think of Lie algebras, you say you want to construct a Lie algebra. You give yourself the Jacobi identities with FABC, etc., the structure constants. The Jacobi identity is a sort of a quadratic equation or a system of quadratic equations. And if you just count equations and variables, you see that it's a very overdetermined system, and it becomes more and more overdetermined when the dimension of the Lie algebra increases. So you have basically equation on variable counting. And so this is supposed to be an equation on, in some sense, an infinite dimensional space. So this is supposed to be, you're going to get very lucky if you're going to get any solutions to this just from this sort of naive argument. And anyway, you know from Lie algebras that nobody finds a Lie algebra by solving the Jacobi identity for the FABCs, but what you do is you realize somehow your Lie algebra as a symmetry of some other object, like a quadratic form or something, and that's how you find them. And so I think to just approach this problem by trying to brute force find a solution to this is just going to be completely impossible. So the idea is, one idea which you can have is that suppose you have one solution. So certainly you can get some solutions, like because free fields provide solutions to this equation, and conformal field theories in 2 dimensions provide solutions. Suppose you have one solution, then a natural idea is to see whether you can find any nearby solutions. So what does it mean? Suppose you have a solution to this equation that depends on a parameter lambda. So you might think of this as a coupling parameter, or it could be actually something like a large n correction to a large n limit, so it would be 1 over n, it might be h bar. It's not really said at this point what it is. So suppose you have a sort of a 1-parameter family of such coefficients, and then they're going to satisfy this consistency condition for all lambda. And then you can ask, what does that mean for these Taylor coefficients, so to speak, of this? So the idea is you have the 0th order one, and you're trying to find the 1st order, 2nd order, so on, in such a way that this sort of, at least in the sense of formal series, is a solution. So that is what is said here. These should be satisfy the order by order version of this condition here. So the and the idea is the lower order condition to some extent determines the higher order conditions. And to get some sort of, it's nice that you can get some sort of more algebraic description of this problem. And that works in terms of a ring. I mean, it's not surprising that some cohomology rings appear here because they're always associated with deformation problems of algebraic structures. So here's a ring which is defined as follows. So we've got step back and we just say generally let's consider chains. That's how this is set up. So these are functions that depend on x1, x2, xn. Analytic, depending on these tensor linear maps for each given x1, xn, they are a linear map to this between this tensor power and v. And dn is some domain. One can write it down what it should be. And then one introduces a linear operator on these things. And this linear operator is defined in terms of the 0th order operator product coefficient. So that's what you're supposed to know. And that's going to define your differential. It's some sort of formula like this, very similar to the Hochschild differential. And the thing is, it's done made in such a way that b squared is 0. So applied b again to this now, then because of the consistency condition at 0th order, b squared is 0. So b squared 0 is the 0th order consistency condition in a way. And then you say, well, now let's look at the first order consistency condition, right? So you have a condition that involves C1 linearly because the original equation is quadratic. So at 0th order it's satisfied, then at first order it's going to give a linear equation for the C1 that will also involve the C0. And if you look at it, it's precisely that b C1 equal to 0. So, right, so you can say the first order deformations are the ones in the kernel of B. That's not quite the whole story because you see if you have an algebra, you're asking for deformations. What you can always do is you can relabel your generators and write the relations in terms of the new generators. They may look quite different, but of course you haven't done anything really. So you really want to mod out by this type of trivial deformation. And so what you do is a deformation in this quantum field theory setting is just an endomorphism Z from V to V. There's lots of gradings and everything there as well, but should all respect that. It's not so important anyway. So if the new deformation, if the deformed solution just comes from relabeling the generators of your original theory, which is a very boring thing to do, then the C1 you can see looks like a B of a Z1, such endomorphism. So you want to take those solutions but mod out by these solutions. So these solutions are automatically solutions to that too, because b squared is 0. So then what you do mathematically, you take this, you look at this quotient space, a standard construction, and this is called a cohomology ring. And so you can say that the first order perturbations of your operator product expansion, or my view is the field theory, is an element of H2. Yeah? Now you want to go on and say, well, first order perturbation theory is nice. You will certainly want to go to arbitrary orders. And then you see you can do that too. And you see that the condition you're going to have to solve is of the form BCI. I is the ith order perturbation you want to find, and even equal to some source W, where the source W is given by the lower order perturbations, some complicated expression. Now you check automatically BW is 0, so this is certainly a necessary condition for this equation to be true. But you want this basically says that this WI, which is what you got from the lower perturbation, is exact. So WI then is an element in H3 because it's closed, but if it's not exact, it's a non-trivial element in H3. So, yes? The C's, yes, the C's are linear maps from V times of V to V.
The CI's are
they're all 2 points. So
how do we get to the subpoint? I mean, I would expect that all the orders.
Yes. You see the B is going to increase so the chain complex is sort of has some.
The order of the perturbation. Yeah.
Right, so it's BC1 has orders, it has 3. So the 3 here is not the order of the perturbation here. It's the fact that this is a 3 form, so to speak. Yeah? So the source of this equation is a 3 form because Ci already was a 2 form. That's the H3. Yeah? Okay, so if this is a non-trivial element, you're not going to get a solution to this equation, and you're stuck. You're not going to get any further, and that's why you call it in mathematics an obstruction. You're not going to get anywhere. And the idea is that if you did this for gauge theory, which had uncurable anomalies, then this would stop at pretty low order. Yeah. So then that would be the sort of interpretation of this. So it's an anomaly. Yeah. So physicists call this an anomaly, something that tells you that quantum theory doesn't exist. Yeah. So you can't go on, at least perturbatively. Yeah. Okay, so now you want to also do gauge theories. Gauge theories, I want to mention this because that is, after all, what people are really interested in. And one wants to really see whether this naturally fits into this. And of course, what is a gauge theory? I mean, I haven't really said how you get the C's, what is the space of fields or something. But in a typical theory, like Yang-Mills theory, you have what is the space V? It's the space of all composite fields, but you want to include also some auxiliary fields, some ghost fields. So you take, a mathematician would say, the free commutative or graded commutative algebra given by all formal expression of this. So D is sort of a formal differential, and then this could be an A mu field, a ghost field, or that kind of thing. And then on this space V, you define your BIS transformation. That's the standard formula for the BIS transformation in a non-abelian theory. It depends also on lambda. And it has also the marvelous property. So here, this is now a map from V to V. And it also has the marvelous property that it squares to 0. So you have another differential. And you want to express the fact that your theory is BRS invariant. So the idea is that the operator product of BIS, so in your mind always replace BIS invariant with gauge invariant. So the idea is the product of gauge invariant fields give gauge invariant fields. So if you say what this means in terms of this S is this condition here. All right, so in general, if you want to step back and see what's the general structure here, you just say, so S is some map from V to V, it squares to 0, and it anti-commutes with some sort of Bose-Fermi grading operator. That's the abstract properties of this BIS differential. And this is then gives a sort of a compatibility condition between the C and the S. And to make this into some sort of cohomological condition, you introduce another differential, now capital B, and it's sort of given by this nice formula here. And then if you look at this, what is you got to get B squared to 0, and it anti-commutes with the B I had earlier, this one here. There's a kind of calculation, a bit longer, not so difficult. So what you can do is you can form what is called the double complex, or the diagonal complex. You take the sum, then this is going to still square to 0, so by the binomial formula basically. And then what you can do is you can discuss simultaneously BRS invariance and this consistency condition in terms of this double complex. Yes, was that? Okay, and then you can just combine everything in one. So that's the mathematical idea. Okay, so now I've said that my viewpoint is quantum field theory is the operator product expansion. The operator product expansion has some properties, but the key one is the associativity law, which takes this form I wrote. And then if you ask for perturbations, you get sort of a cohomology interpretation or formulation of this, what this is. But cohomology is nice, and I told this to you because I thought it was maybe appeals to some people's sense of mathematical elegance or something. I don't know. I mean, it's all, of course, very education dependent. But it doesn't really, I mean, cohomology is nice if you have some way to calculate cohomology rings, like exact sequences, things like that. And you can write down some exact sequences here, but I don't think, I wasn't able so far to directly calculate, let's say you start with a free theory, directly calculate these rings, parameterizing the deformations from some sort of exact sequences, which you can write down. It's not a problem. But I wasn't able to, and I think it's more like, as I think maybe also John said in his talk, this cohomology is really more a language here, and it's not really, I don't see, I mean, I have some ideas, but I don't see, it's not obvious to see how this helps you with the solution of the problem of actually finding a solution to this big consistency condition here, even perturbatively. Yes?
This looks like the entire cyclic cohomology, and your solution would be the JLO cosine.
Yes, it's still not. I think it's a bit different because it doesn't have the cyclicity type property. I mean, we can talk about it later. I also thought that it might be. I know what your cyclic cohomology. I think it's something different though. But it has many things in common though. But all right. So now, where was I? So I want to put another twist on this, and this was noticed by myself and my student Heine Olbermann, who did the part of the work with me that is now going to follow. So PhD student, and so what? Is this turned off? And it's turned off again? Or? Yeah. All right. Oh wow! It's like in a theater. All right. So you just repackage this a little bit, and it doesn't look like much really. To start, I mean, you just say, now this is an object with 3 indices. It depends on 2 points, but if in a translationally invariant situation, it depends on the difference. So I just put in 1 point. And then I just say, well, for fixed A, this is an object with 2 indices. So it's a linear map. It's like a matrix. And so I just say, for fixed A, I call this matrix Y. So more precisely, I mean, if in some sort of bracket type notation, if the basis vectors of V are called phi A, then the right side is defined by this left side. Yeah? So it's a definition of Y. For each phi A, where each choice of basis, you get an endomorphism whose matrix elements are given by this. It's just like you pass from Aij matrix notation in sort of undergraduate algebra to A or something. Yeah, this is that kind of thing. So because I'm lazy, I don't want to write phi A, I'm just going to write A. So this is supposed to be basis vector now. And I call these vertex operators. Why do I call them vertex operators? So you see, these C's, I still haven't told you how to get them, though. Like this should be familiar to you in algebraic quantum field theory. You have lots of things, but nobody tells you how to get them. These satisfy this consistency condition. And clearly, you're going to get a corresponding condition here for the Y. I just wanted if you just ask, it's just a completely straightforward exercise just with indices, and that's the condition here. So it's on this domain, you have this condition. So now Y depends on a space-time point X and a vector, a vector representing a composite field. And if you multiply them, you get this. So it's a quadratic type relation, as it should. There are also other things you get. So this is, you can make this as some sort of fancy definition, but basically for us, that's the condition you have on this domain here. Same condition, just different letters of the alphabet, so to speak. But it looks a bit different, and it sort of gives you some ideas what you can do, and that's what was useful. So why is it called vertex algebra? It's called as that name because there is a sort of a branch of mathematics that, or sort of constructions in mathematics that are called vertex algebras. They are very famous and have been used mainly in two-dimensional CFTs, and I would say exclusively. And they basically postulate a relation that's formally equivalent to this one. So I say formally, there's some subtle differences, but I think it justifies this same name. So, but I don't assume conformal invariance or 2 dimensions or anything here. Right. So I still want to get some solutions, And so also the only thing I could come up with, at least perturbatively, is to say, well, after all, it starts with a free field theory, and what on earth could you have other than a coupling constant? So you just say, well, let's suppose classically I have a field that's described by this nonlinear equation. Lambda is my coupling constant, and I try to calculate sort of the vertex algebra associated with this theory perturbatively in lambda. So 0th order, you have the free vertex algebra, so the free operator product expansion of the free massless Bose field on Euclidean space, well known. You calculate your y's from that, just an exercise, but you want this one. So if you say that this is sort of an equation for composite quantum fields, you can multiply by another quantum field, and you get a heuristic equation that you believe must be true for these vertex algebras. It looks like exactly the same equation. Yeah. But it sort of comes from the OPE. So the idea then is to say that, well, my perturbation ansatz is this, so I'm going to write this as a formal series, and y0 is my 0th order term, and then that's the free field, and then higher order contributions. And I want these things to be true. That is, I want my consistency condition. I now write it straight away in terms of the ith order contribution, and I want my field equation, and that's this, because you see lambda gives you, increases the order, so to speak. That's why you have I minus 1 here and I. So my claim is that, so before I had just this, but now I also have this. And my claim is that if I put these together, I get really a scheme for calculating these perturbations. And how does this work? So basically, this is the equation to look at first. So let's say you have the 0th order guy, so I is 1. Then by inverting block, this is the Laplace operator. I'm a bit sloppy here. This is not the wave operator. I get y1, and that gives rise to an obvious reduction. But the thing is, so that's what is written here. So y0, if you have that, the free theory, you get this. But the problem is now you want to go next, you want to repeat this and now put y1 here and y0 there. And but you don't know y1 of the composite field phi cubed. You only know y1 of phi. So it looks like you're completely stuck. You're not going to go anywhere with this. And now is the trick. Now is where the consistency condition comes. Oops. So let's just do phi squared first. You show that y1 squared, and next you're going to do y1 cubed, or y1 squared first. Using the consistency condition, you can write it as some sort of limit like this. And on this right-hand side, the thing is you know everything already. So you have a way, now you do phi cubed, etc. It's a similar formula. So this is sort of the formula, and these things you subtract. They just the left-hand side, the right-hand side of this consistency condition to the appropriate order that's relevant in the limit. They're called counter terms. So not counter terms in the sense of renormalization theory. They're more like what Reiner said, this Hadamard subtraction, and that's sort of the generalization of this Hadamard subtraction. All right, so you do this, and the idea is you do this, and you start from the free field, and you crank out more and more terms, and you see what you get, and you define a vertex algebra in this way for this lambda phi cubed theory. Lambda phi 4 would be the potential. Okay, so first you have to find some decent parametrization of the space of composite fields, and so it turns out it's going to get a complete mess if you don't have a nice basis there. And what you do is you take spherical harmonics in d dimensions, you put in a derivative operator, and then that gives a basic field with derivatives, and then if you take products of this, you get all fields, and then your LM are supposed to give you the labels of the composite quantum fields. And what turns out to be convenient is to think of this space V as some sort of a Fock space. Has nothing to do with the true Fock space of the true Hilbert space. It's just a made-up Fock space of whose elements are in one-to-one correspondence with your composite fields. Anyway, it's convenient to think about it that way. And then that's the rules. So this one operator plays the role of the vacuum, and then this is sort of the B plus by definition creates this, and this annihilates by definition that, and you impose this. So you generate, you give your space the structure of a Fock space. Certainly nobody can keep you from doing that. That's your business. It just turns out to be convenient. And then the good thing is this should be a Y0. The free field vertex operator then has a nice simple form in terms of creation and annihilation operators. Yeah? So I should emphasize this is not a new theory, quantum field theory I'm cooking up. I'm just taking the standard free bosonic field in Euclidean dimensions. I compute its OPE, and then I repackage that information in the Y, and this is what I get. I don't make this up or something. It's something you calculate with some effort. There are some definitions. Yeah, S are these harmonic polynomials, as they're called, or spherical harmonics in D dimensions. All right, so this is your starting point, and then here's your field equation to get the first order. Now you have some R is the radial coordinate. You have some Laplace operator to invert on this. And now the next trick is you just invert this algebraically. So you just write down the inverse on the class of functions that are radial powers times harmonic polynomials. Then it becomes a purely algebraic problem. Just like inverting the Laplace operator on e to the ikx is very easy, right? So it's something like that. And right, so you do this, you go to second order, you do some similar thing. You could do it for a general interaction, so not just convenience here. Anyway, you get some sort of iterative process in that way, where you always get the I plus first order is always some triple product like this involving lower orders with the inverse of the Laplace operator and some counter terms, which can be a bit complicated, and I didn't write them down. So if you look at this expression, I don't know if you're already very tired or something and you don't want to look at it anyway, so that's if you look at it and you're a bit familiar with this type of expansions, you immediately see that that's how you should think about it. It's the three factors here are the roots, so to speak, of some sort of elementary tree, and this factor is the new guy. And then obviously if you repeat that, you're going to stick these things together and you build up a tree. Yeah? That's the origin of the tree, the trees that appear in sort of, if you do Feynman diagrams that, without loops, and you're going to get tree diagrams. It's kind of that kind of tree that appears here. It's also related to these Galavotti-Niccolo trees, and some people probably know this kind of stuff anyway. So you build up a big tree, and then you get a representation of the ith order vertex operator by sort of a sum of trees, and the incidence number of the tree is as usual given by the type of the interaction. Right, and then you work out what this Laplace inversion and all this, what this amounts to, and this is somewhat of a headache, but you play some nice residue tricks and you do various things, and you get some sort of rules for the nth order perturbation of this vertex operator. And so the rules are you write down lots of trees with n vertices, and in fact all of them, and then there you have lines, and the lines carry some, these are some sort of hypergeometric functions with some certain factors, and the vertices carry some sort of delta function. These indices nu ij are complex numbers. Then you have some delta I, they're sort of small numbers. You later take a residue of those. In those, you get certain things for the endpoints of the leaves of the tree, so to speak. Well, it's like a bit like Feynman rules, except that there are no loops at this stage, just trees. And you have, this is a bit like a propagator, just the angular part. Isn't it? Okay. Right, so we write down all these factors, then you integrate over these intermediate points over a sphere. You integrate over these numbers, complex numbers. You take some residues in the end, and you take some sums, and you get a big fat expression. You would have never guessed this would be the solution to your consistency condition in the first place. but that's what you led to. This is an example. Doesn't look very nice. Yeah. So these are basically residues. So you have a fourfold residue which you have to take in the right order. Here are your angular integrals, and then you have these hypergeometric functions and a lot of creation. So this would be one contribution to this vertex operator at order 3. Okay, now there are various other representations which you can derive for this. This one is the one in terms of Legendre functions, really, these P's. Then there's another representation which is purely in terms of sums, and that gives functions of generalized hypergeometric type. And I think that together, so the idea here is you have your operator product expansion, your consistency condition, you find a perturbative solution, then this perturbative solution is given in terms of certain special functions, like a class of sort of things you can think of as quite generalized hypergeometric functions, but the consistency conditions give you a lot of functional relations between these functions. You get that. And that's in that sense they're special, I think. Anyway, if you want to get a taste of this, so you get this, this is a matrix, it's yet another basis. So why is it called hypergeometric? Because, well, it has some residues here as well. So you always get a gamma, gamma, gamma functions everywhere. This is that typical type of hypergeometric functions. You derive that. Takes some time. Anyway, there's another representation which is in terms of graphs that are actually loop graphs, and they arise in a certain way, and what you get is some sort of triangulated surfaces, and your vertex algebra as operator has sort of basically 3 indices, or your operator product coefficient C, A, B, C. And this can be written as a sum over surfaces with holes. I mean, that idea is quite closely related to what you do with Feynman diagrams, as sort of a genus expansion. But then you also have, instead of the angular integrations you have on these triangles, you have sort of things like 6J symbols for SOD, 6J, 9J, and so on. It makes it a bit similar to what people in loop quantum gravity, what I've seen there, these spin foams, which are also structures like this, which are labeled by representation data. So, but I don't, in this case, it's the origin of these 6 or 9J symbols are just the sort of angular integrations. But there might be some interesting connection, I don't know. But these are certainly not topological models or anything. Right, I wanted to, I think since you're probably all hungry, I wanted to conclude here, and I wanted to just try to emphasize again what I've tried to present to you in the spirit of the approach that Bob presented to you, our sort of a joint idea. I thought what was a good idea was to take algebraic quantum field theory maybe more seriously than algebraic quantum field theorists, and take it really as a constructive tool. So you don't say, well, you do all kinds of other things, auxiliary constructions, and at the end of the day you get your algebras. I thought you just start directly with the algebras and try to compute the algebras directly. That was sort of the philosophy. And you have to get a handle to compute an algebra is, what is this? So you have to get something to get your hands on that you can do things with. And the only thing that I could think of, and Bob, we together, was this operator product expansion. And that turns out, when combined with field equations and when combined with this consistency conditions, does really allow you to do calculations. And you see in this not very nice, but well, nice depends on your viewpoint again, but very explicit formulas, right? So this is what I'm saying here. So perturbations can be characterized intrinsically. That's this Hochschild cohomology business. I think it's a nice language, as now doesn't give you particularly new methods to actually solve the problem. But one nice thing, well, there's the issue of renormalization, and that's interesting here because that's somehow taken care of automatically. That's the idea, because you automatically get counter terms. It's not something you have to impose or something from the outside. It's built into the whole thing from the start. I like that about it. Yeah, so I think what I really thought this might be interesting was that I too have the dream to one day win this $1 million Clay Prize, and that unfortunately asks for a non-perturbative solution. And I thought with Bob together, we thought that maybe because this operator expansion has sort of less information really than the whole thing, it also probably has less of the difficulties. I mean, all this physics that of QCD and gauge theories is really in the vacuum state or the states, and the states that are not considered when you do the operator product expansion at the first stage. So we thought we had a better shot at maybe getting another way to do non-perturbative quantum field theory. I must say that as so far I haven't really been able to. I certainly have some ideas, but I haven't really been able to fulfill that promise. Except for, and I'm sort of not sure how far one can really get a non-perturbative solution to this operator expansion. It's certainly possible to get numerical bounds using something like the Wilson-Wigner-Polchinski flow equations, but it's not. I didn't have a good idea as yet how to do this non-perturbatively, and I guess I have to wait for the $1 million for another 50 years until maybe. Anyway, so this I want to conclude here. I think I'm also used up my time. Thank you very much.
Thank you for a very beautiful talk. Are there questions? Many.
You say renormalization is not needed, but can you impose normalization conditions?
Yes. So what is there, of course, is the sort of finite renormalization ambiguities, if you like. That takes the form of field redefinitions. So the idea is that if you were sort of a perturbative guide using sort of Feynman diagrams, you'd find these finite ambiguities, and the statement would be that they can all be absorbed into redefinitions of the coupling constants and redefinitions of the fields. And those that freedom you have here anyway. So I think probably that's the same amount of freedom. But I quite frankly, we're only starting this. I haven't really, I cannot prove it, but...
you seem to have the freedom, but you have to be able to impose a condition on a low energy norm.
Right, but I think the conditions that people usually impose, I mean, they relate to states, and what you basically want to say is something like, right, I think that's a really good point, and I think lots of the, so, yes, so how do I, so in the Lagrangian, well, I wrote a field equation, but of course you can write a Lagrangian, something you have for. Now I put in a mass just for the definition. So you want to somehow say that this parameter m squared is the physical mass of the theory, right? Now the physical mass really is defined not by this bogus thing in the Lagrangian, because that's just your starting point. Your physical mass is defined by you take some phi of x at sort of a space-like separated points in the vacuum, say, and you say this goes for large distances, this goes like minus m. I call this MP, m physical, yeah? So this is in position space, you can write it in momentum space. But the idea is if x1, so this is the definition of mass. And you want to, the renormalization condition is that this m that appears in your expansion be equal to that m that appears here. Yeah, so that's the renormalization. But you clearly see this is going to involve the state, right? And so with the other renormalization condition of this lambda. Now, I don't want to do that particularly because I don't have states to play with in the beginning, and I think in a way that's an advantage because there are lots of complicated physics going in the states that I don't have to deal with. So I can make up some complete bogus renormalization condition where the beta function vanishes up to its first 3 coefficients or something. That's all okay in this approach. Yeah. So I should say in a curved space. I mean, this is not in a curved space, but in a curved space, you wouldn't be able to write this down in the first place anyway. So I don't see any particular. I mean, it's very practical because an experimentalist wants to, he has some formula with m, and he wants to make sure for cross section, he wants to make sure that m is actually the physical mass and not some parameter that's related to that by some complicated function. But as a matter of principle, I think that is not so really that important.
Are there other questions? Yes.
Well, when you have a field equation like the phi-cube equation to start with, then it entails other field equations like the conservation of the stress energy tensor or whatnot. So in your list of fields, which you suppose to be a basis of the Fock space, there are actually linear relations among these, these objects.
Yes.
And some basis vectors are missing or independent of each other.
Yes.
So is this obviously should produce some problem?
It doesn't produce a problem. It produces. Yeah, it doesn't produce a problem. It produces the difficulty. I mean, it. Okay, so the real way to do it, and is to work in a formalism where, like, I think what you're referring to. Here's my space of fields. So now I might, in this space of fields, there might be a field like phi to the 7th log phi minus lambda phi cubed. Now, that's my field equation actually, and so you better say that, well, if that's supposed to be 0, you better say that the field phi block phi is the same as the
the trouble it mixes the order of the perturbation.
That's right. So the way we do it is that this thing by definition never is in there. So it's always this is always the representative, right? Now a better way. I think this is because we started doing it that way, and the better way I think is to work with everything. Don't factor by any ideal. I mean, basically, I heard someone say from the audience, factor by Robert. Yes. So basically, you factor by an ideal, but the ideal basically has to come out of perturbation theory itself because of all these anomalies and something. So a better way to do it is to not factor by this ideal, and then there's a nice way to deal with it when you introduce yet other auxiliary field, so-called anti-fields. And then you work with everything, and at the end, you factor by the ideal using some cohomology stuff again. Yeah, so that's basically what you do. But the differential there, this new differential that takes care of the relations, that's computed, so to speak, in the construction process, and then in the end, you put just yet another. That's a third differential now already, and you have no difficulty to introduce a fourth and so on, but I didn't want to do it. But that would be the right way to do it.
So let me ask a question. I asked before about this cohomology.
Yes.
It seems that your diagrams also reminded me of the diagrams I saw Durkheim draw when he explained his Hopfeld.
Oh, yes.
What is the connection?
Yes. I think. Right. So many people draw diagrams, of course. Yeah. So. Also, no, everything. Yes, and it's not really that surprising. You get trees. No, I don't. You can. Yeah. You can. I mean, these counter terms can be organized by a Hopf algebra. I mean, the combinatorics of these terms that I've written in dots or something, they can be, their combinatorics again is governed by a Hopf algebra. Yeah, you can do it that way. I don't think you get that many insights from that, but if you so like, you can. It's just a combinatorial level, yeah. So, but you're completely right, I think. Yeah, it's more like the Hopf algebra of rooted trees. I mean, that's really no. I mean, I don't know. I mean, I don't know. I think Kon-Kramer stuff, that's interesting. I don't think in this context you can introduce Hopf algebras to make your combinatorics look algebraic. I mean, say, but I don't think it gives you that many additional insights, I would say, into the problem.
Are there any other questions? Yes, Klaus.
You apply this to the Euclidean framework.
Yes.
The Euclidean framework, we have an abelian algebra.
Yes. Yeah.
What is the content of your algebra?
Well, it's not really the. I mean, it's not really. I mean, it's more like because you have a reference point. I mean, it's not really actually an algebra in like it's some structure that's reminiscent in many ways of an algebra. So so it's not abelian. I mean, you can't really talk about that. I mean, one way to see this is you have a. If I write this, this is. So here's my consistency condition, which if right. So you would ask why? I mean, abelian would mean I can flip that one to the other side. But the problem is that's only going to converge. I mean, this involves a domain issue. You want to apply this to a vector C, let's say, and for this to be defined at all, it is necessary that the modulus of x be greater than the modulus of y. Otherwise, you can't even write. You can formally write down the other way, the other thing, but then it's meaningless. It's not in the domain. Yeah. So so people in vertex algebras in sort of 2 dimensions, they get around this by saying, well, they're not actually doing analytic function. They're not working in the category of analytic functions, but they're working in a category of formal Laurent series. And in that category, you can actually turn this around and you get a slightly different version of this. But you can't do the category of formal Laurent series for generic field series because the coefficients have singularities that are much more general than 1 over x or 1 over x squared. I mean, you have logs, you have all kinds of things. So you can't. So I think, yes, it is in some sense. It's not clear. It's not really. I think it's misleading to call it an algebra. As, it's not really fulfills the axioms of algebra as you read them on page 3 in some algebra book or something. But it's that's why it's called, yeah. But for the analytic continuation, that can be easily done in practice because then at each finite order, this y involves r to some maybe -10 and log r to some 15, and r is the Euclidean distance. Now, just to make that into the Lorentzian distance with the right I epsilon, and yeah, that's it, basically.
So I think that you can take the constructive field theory examples in 2 and 3 dimensions as examples of your algebra, which are non-perturbative.
Oh yeah, I think so too. I mean, the question would be to really verify. Yeah, I think so. We've been I think so too. But we would have liked to get some. Our motivation was not that we thought, our motivation was really if you had a really Lorentzian, or sort of was to look at this from the other side, rather try to, at the end of the day, construct the field theory from sort of a purely algebraic viewpoint, and then maybe to compare to what you and all the other people did. So it's complementary, I think, but it's the same theory one is talking about after all. Yeah.
Are there other questions? Well, let's thank the speaker for very interesting.
So,